let's use what we've learned about finding the minimums and maximums of functions to solve some optimization problems. And you might be wondering, Sal, what is an optimization problem? And my reply to you is, well, the problems we're about to do are optimization problems, and I think you'll understand why they're called optimization problems. Anyway, so the first problem is find two numbers whose product is negative 16. So the product is equal to minus 16. And it says, and the sum of whose squares is a minimum. So sum of squares is minimum. So if you haven't figured it out yet, these optimization problems they'll all impose some type of constraints and then say, so for what numbers do we get a maximum value or a minimum value? Well, really, usually just maximum or minimum. So let's do this problem, and then we'll do a couple more. So two numbers whose product is negative 16, and the sum of their squares is a minimum. So let's just, let's call those two numbers x and y. So the product is minus 16, so we know that x times y is equal to minus 16. And then what's the sum of their squares? So let's just say the sum of squares. So I'll just call that s. The sum of their squares is going to be equal to x squared plus y squared. And so this is the function that we want to optimize. And in this case, we want to find the minimum value. So how do we do this problem? Well, the first thing we want to do, we want to minimize this function, but right now it's a function of two variables. And we haven't done multivariable calculus yet, so it would be easier if we just found, if we could express this as a function of one variable. And then we could optimize it with respect to that variable, and we could substitute backwards, et cetera, et cetera. So how can we write the sum of the squares as a function of one variable? Well, that's where this equation comes in handy. We could substitute either for x or y. Let's just substitute y. So we could rewrite this equation, dividing both sides by x, as y is equal to minus 16 over x. Right? So if we take this, I just divided both sides of this by x. If we take this and substitute it here, we get the sum of the squares of the two numbers is going to be equal to x squared plus y squared. Well, y is this. So what's this thing squared? Minus 16 squared is 256, and over x squared. So that's the sum of the squares of the two numbers. And so how do we learn to find minimums or maximums, or in general optimize a function? Well, in general, a function hits a minimum or maximum point, especially a local minimum or maximum point, when its derivative is 0. So let's take the derivative of this and set it equal to 0, and hopefully we find a minimum point. And then we'll later show that it really is a minimum point. So let's take the derivative of this with respect to x. I'll just write s prime. We could have written ds, dx, but I'll save on notation. Save on my electronic ink. So s prime is equal to, so this is the slope of this function at any time, at any x, 2x plus, this is the same thing as 256 times x to the negative 2, right? So what will be the derivative? The derivative is going to be 256. We multiply by times the exponent, which is minus 2, and then we decrement the exponent by 1, so we get x to the minus 3. So the derivative is equal to 2x plus, no, not plus, 2x minus 512 times x to the minus 3. And we want to find a local minimum or maximum, or maybe a global one. So we want to figure out where the slope is equal to 0. So this is the slope. So let's set this equal to 0. So we get 2x minus 512 x to the minus 3 is equal to 0. Let's see, we can manipulate that around a little bit. We get 2x. Let me do it in a different color. I'm tired of the yellow. We could then, whoops. So you get, just going up here, we get, just let's add 512 to both sides. So we get 2x is equal to 512 x to the minus 3, right? I just added 512 to both sides. And let's multiply both sides of this equation times x to the third, just to get rid of this. So if we multiply both sides of the equation by x to the third, we get 2x to the fourth is equal to 512. Right? X to the third times x to the minus 3, that just equals 1. Divide both sides of this by 2, you get x to the fourth is equal to 256. And if it's not immediately clear what this is, x is going to be the fourth root of 256. If you don't know that immediately, you can think, well, what's the square root of 256? Well, it's 16. And then what's the square root of that? Well, the square root of 16 is plus or minus. So the square root of this is plus or minus 16, but then the square root of at least the plus 16 is plus or minus 4. So this x is equal to plus or minus 4. And if you don't believe me, take either minus 4 or positive 4 and take it to the fourth power, and you will get 256. So if x is plus or minus 4, what is y? Well, we just know that y is minus 16 divided by x. So let's say we could get x is 4. If x is 4, then what is y? It's minus 16 divided by 4. Then y is equal to minus 4. And of course, if x was minus 4, then y is minus 16 divided by minus 4. Y would be equal to 4. So it actually doesn't matter which one we take. The two numbers are 4 and negative 4. It doesn't matter what we call them, x or y. The two numbers are 4 and minus 4. And we are actually done the problem. These are the two numbers where the sum of the squares. Well, actually, no, we are not done. We know that we've reached some type of minimum or maximum point here. And since they asked for a minimum and this was the only point that we found where the slope was 0, we probably solved the problem. But let's prove to ourselves that we're really at a minimum point on this function, when x is equal to 4. And how do we do that? Well, we could take the second derivative of this function, see what the second derivative is at x equals 4, and then see if we're concave upwards or concave downwards. So this is the first derivative. This was the first derivative. That's the first derivative. What is the second derivative? So s prime prime is equal to, what's this, 2, and then we'll see minus 3 times minus 512, so that's plus, and what is that, 1536? Right, plus 1536 times x to the minus 4. Right? So, what is s prime prime? I should be writing s as a function of x. I shouldn't be lazy with my notation. These are all as a function of x, but you get the point. So what is s prime prime when x is equal to 4? Well, it's equal to 2 plus 1536, and then what's 4 to the minus 4 power? Well, it's 1 over 256 times 1 over 256. And we don't even have to calculate this. All we care about is this value positive or negative, and it is clearly positive. We have a positive number plus a positive number divided by a positive number, so we have a positive number here. So, what do we know? We know at the point x is equal to 4, this function here, our sum of squares function, is concave upwards. And we know that because the second derivative at x is equal to 4 is positive. And what does concave upwards look like? Concave upwards looks like this. And so x equals 4 is there, and so we are at a minimum point. And so we know that the sum of squares are minimum. And if you really want to make sure that you're not missing something or we haven't done this wrong, think of other, just play around. Think of other numbers whose product is minus 16 and figure out their sum of squares. And I can pretty much guarantee you that it will be larger than the sum of the squares of minus 4 and 4. And so what are they? What is s of 4? What is the sum of squares of 4 and minus 4? It's 4 squared is 16 plus 16 is 32, right? That's the sum. So let's try some other numbers. What is the sum of 1 squared plus, I don't know, minus 16 squared, right? Those two have the product minus 16, 1 and minus 16. That is equal to what? 257? Much higher number. You could try negative 8 and 2 or negative 2 and 8. And everything you'll find will have a higher sum of squares than 4 and minus 4. Anyway, I was actually planning on doing 3 problems in this video, but I'm reaching the 10-minute limit. So I will finish this video now, and I will do 2 more of these optimization problems. See you soon.